Hi, my name is Doyeon Kim, and I'll present my work titled mToFNet, Object Anti-Spoofing with Mobile Time-of-Flight Data, co-authored by Yonghyun Jeong, Jongwon Choi, and others. The outline looks like this. We will start off with a brief introduction of our work, then move on to the dataset, and then go into the details of our approach and framework, and conclude with the results of our study. First, let me briefly introduce the background and motivation of our work. In online markets, sellers can maliciously recapture others' images on display screens to utilize as spoof images, and buyers are forced to bear the risk. To prevent such harms, many online services provide mobile applications developed for secure capturing and direct transferring of users' images. However, such verification methods are still imperfect because the scammers can avoid the safeguards by recapturing others' images on displays. To detect such cases, much effort has been put in to develop a model to distinguish between real and display images. However, the moiré patterns varying by the display type can cause the model's overfitting issue. As you can see in the second row of Figure 1, the moiré patterns are distinctively shown for each display type in the etched images. The diversity in patterns makes it more challenging to develop a generalized model for detecting any type of displays used for online scam. Despite the difficulties, the generalization issue must be overcome because it is impossible to forecast a possible display type that may be used for scam in advance and utilize it to pre-train the model. Next is a dataset collected and used for our work. For robust generalization, we utilize both the image and the depth map obtained with a mobile time-of-flight sensor. As you can see in Figure 2, the difference between the real and display images becomes much more distinct in the ToF domain on the right compared to the image domain on the left, as indicated in the graphs. This is why we collect mToF dataset, which is the largest and the most diverse object anti-spoofing dataset with paired images, and the first to utilize ToF maps in this field of study. We use a smartphone with a ToF sensor to capture 12,529 images in 27 categories on 16 different spoof media, including the monitors, laptops, mobile phones, tablet PCs, and projectors. Up next is the approach and the overall framework of our study. The framework contains dual embedding models to learn the multi-sensor representation of the real images. Since no display image is used during training, the model can ignore the moiré patterns to overcome the overfitting issue and achieve robust generalization across various spoof media. Using the real images and their paired ToF maps as the input, the first embedding model is trained to reconstruct the ToF maps. Then, using the sample ToF maps, the second embedding model is trained to reconstruct the identical ToF maps. The representation features from the two embedding models are mapped into the identical feature space, from which the classifier makes the prediction between real and displays. Next is the experimental results of our method. The table presents the performance of various methods to the unseen media when only one display is considered for training. Target display experiments are of the models trained and tested using the same display types. Also, unseen display experiments are of the models tested with the unseen display types, while all display experiments are of the models tested with all display types. Our model achieves the best overall performance in all three types of experiments, compared to other benchmarks, as highlighted in the last row. This concludes my presentation. Thank you so much for listening. You can check out more information on our work at our GitHub, as indicated in the address at the bottom of this slide. Thank you.